In this video, we will be talking primarily about Venn diagrams. But before we jump into the Venn diagram, I want to take a minute and talk about a card game called Set. And some of you may have heard of this card game, but this is a game that's about identifying sets and recognizing sets. And as you can see, we have cards, and they have different attributes. They have different shapes. We have diamonds and these oblong shapes and these squiggly shapes. And we have colors. We have green, red, and purple. We have also shading types. So we have solid shade, we have line shade, and we have no shade or open. And so when we're looking for a set, we're looking for three cards. Sets are size 3. I guess we would say their cardinality of a set is 3. And those 3 cards have to either be all the same with regard to a particular attribute or all different. And so let me see if I can find a set. Actually, I found one. So we got one here, here, and here. And notice that's a set because the shapes are all the same. They're all shaded solid, they're all purple, and the number of elements is different on each card. So we have a 1, a 2, and a 3. So this would be an example of a set. See if I can find another one. So we've got, so I see 3 colors. I see green, purple, and red. But that's not a set quite. So I'm thinking we've got purple with lines and one shape, red with these oblongs and solid. Now I need 3 that are open, different. Okay, so if this was green, that would be a set, but it's not green. So again, looking, diamond, that's green and solid, single swiggle, that's open. I'm not seeing another one to match that. If that was purple, we'd have a set there. I'm going to put 3 cards out just to expedite this. There might have been a set with those other cards, but let's see if I can find another one. Purple, red, green, but that doesn't quite do it. Oh, okay. Green, red. If you're sitting there behind your computer, jumping up and down saying, I see a set, but I can't push a button, I apologize for not seeing it. I am not seeing another set. Let's see, green, purple, red. Oh, if that was, oh wait, no, shoot. Purple, green, red. Oh, that's the same, those shapes. Purple, green, purple, green. Oh, there should be a set here. Purple, red. Oh my gosh. Trying to make my life easier, adding more cards. Oh, there's got to be a set here now. Let's see. Okay, you might want to fast forward through this part, especially if you're really getting frustrated with me saying, oh my gosh, I see one right there. Why can't he see it? Oh, Todd, come on. All right, there's one red, there's purple and diamonds, and oh man, green. Okay, well, I'm going to come back to this after I finish the video and find some more because I don't know why I can't find them right now. But in any case, it's a fun game to play with your kids. It's a fun game to play as an adult, and I think it builds a skill. It builds an ability to do math, see patterns. A lot of math, especially in algebra, is about seeing patterns, like terms. And knowing when a number is constant. I mean, there's just a lot of areas in algebra where you use this pattern recognition, and other places in math as well. It's not just algebra. And the Venn diagrams that we can look at are also another area where we might be looking at patterns. In any case, the Venn diagram is named after an English mathematician named John Venn. This is a stained glass mirror that is a tribute to him. I'm not sure exactly where this is. I wonder if it's in the somewhere in the Royal Society Church. I don't know if they have a church, honestly, but I don't know where this is. But it's a tribute to John Venn, and I found it on this image. I thought it was kind of neat. Anyway, John Venn lived, during the late 19th century, early 20th century. So he lived right about the same time as George Cantor. Set theory was just really becoming a discipline. Lots of controversy around it. Interestingly, I don't think John Venn was caught up in the same kinds of controversies as George Cantor, for example. I tell his story a little bit on this week's homepage in Canvas. But in any case, here's the math definition of a Venn diagram. A Venn diagram represents each set by a circle, usually drawn inside of a containing box representing the universal set. Overlapping areas indicate elements common to both sets. Here's an example. Here's an example of a Venn diagram, and these are some foods. And the sets are foods eaten in the morning and foods eaten at night. There's, I'm sure, going to be some differences in people's preferences, but this is something, an example of something that we could investigate in terms of being, questioning whether there's an overlap here. You can see this is the classic Venn diagram shape, the universe of foods, and then we've got one category, which are foods eaten in the morning, or one set, foods eaten at night. And I could one thing we can do is see that strawberries here should be written in this part of the intersection, because both sets contain strawberries, as do both sets contain tomatoes. And so, probably a better way to draw this diagram actually would be to put, maybe they didn't do it because it wouldn't fit, to put strawberries instead of in both sets like that, to put them in the intersection. And we could put tomatoes in here. And for me, another thing I would put in the intersection are potatoes. I like potatoes. I like them in the morning. I like them at night. Eggs, I eat them in the morning. That works. Bacon, morning. Pancakes, always in the morning for me. Leftover pizza, sure, that's not a morning food for me. Although I know some college students and even my kids might put that in the intersection. Leftover pizza could be a food eaten in the morning for sure. And so again, you could create this kind of a Venn diagram for yourself. Everybody would have probably their own Venn diagram when it comes to, foods and sets of different types of foods and when they're eaten and not eaten and so forth. Here's another example of a Venn diagram that seems appropriate in today's world. Social media, it's a big thing. Lots of people are using it now. And there's two major social media. I mean, there's also, I know there are others, but Twitter and Facebook are two of the really popular ones. I know Instagram is out there now, and we could probably, we could add a circle for Instagram and make up some names. But I want to really kind of focus on analyzing this particular Venn diagram. And for shorthand notation, I'm just going to label the Facebook set with an F and the Twitter set with a T. So we have set F, which are all these people who use Facebook, and we have set T, which is all the people who use Twitter, and then we have our universal set, which is indicated by this box. And we can talk about some of the symbols that the book has. I'm going to change my pen color there. It's not going to show up very good. So we could talk about some of the symbols from the textbook. Like, for example, F, this upside down U means intersection. T, so if we thought of the F intersect T, then the set would contain one person. In this case, it would be Bob. We could also talk about the union of the set. F, Facebook users, union, Twitter users, would be the set containing Al, Courtney, Freda, Bob, Dave, Ernie, Gary. That would be the union. It's all the people that use Facebook and all the people who use Twitter. So, and that's one thing we can also keep track of. We can think about how do we say that. With the intersection, the conjunction we use is or. With the union, it's and. So to be in the intersection, you either use Facebook or Twitter. Oh, yeah, I got that backwards. Shoot, I'm glad I noticed that. I say that backwards sometimes. Let me correct that. So the intersection, the conjunction is and. So to be in the intersection, you have to be a Facebook user and a Twitter user. And notice there's only one person in the intersection. The conjunction we use for union is or. And in math, we always think in terms of the inclusive or, not the inclusive or. So to be in the union, you are either a Facebook user or you're a Twitter user. Now, interestingly, we could also talk about the union of F union T, and this would be again what we were just talking about above. And I'm put a little C up there for complement, because the complement of the union of Facebook users and Twitter users would have one person in it, and that would be Harry. This is a really common Venn diagram we see in mathematics. This is the universe of the numbers that we use. And this actually, it's interesting because this universe of numbers will take us all the way to, this takes us all the way to, well, certainly this universe would take us through college algebra. So if you, I got to slow down for a minute and think about how to spell algebra. College algebra, so this would be our universe of numbers for college algebra. I want to write calculus down, but that's not necessarily the case. It depends on how far you go in calculus. Early semesters of calculus, this could be the universe of numbers. So these are all the rational, irrationals. This is a set of real numbers, by the way. We give it a name in mathematics. And so here we have all the rational numbers. These are numbers that can be written as fractions, like 1/2, 10/3, and so forth. Integers, these are, like, it might be actually easier to start on the inside here. These are the natural numbers. These are the count, and sometimes we refer to these as the counting numbers, but like 1, 2, 3, 4 out to infinity. Then we have the whole numbers, which is, and you can see the set of naturals is a circle within the set of whole numbers. So that means all natural numbers are whole numbers, but not all whole numbers are natural numbers. And the difference is 0 is included in the set of whole numbers. And then outside those two circles are nested in another circle called the integers. And all natural numbers are integers, whole numbers are integers, and the other numbers that are in the integers are the opposites. I think I'll change my pen color again real quick here because it's not showing up very good in the integers. So like -3, -2, I'm just counting down, but all the negative opposites of all the natural numbers would be part of the integers as well. And then we also have this other set of irrational numbers, and you notice there's a split in this Venn diagram. So the set of rational numbers and the set of irrational numbers are what we call disjoint sets. The intersection of rational numbers with the irrational numbers is the empty set, and there are no numbers in that set. So a number is either rational or it's irrational. And in fact, the idea of irrational numbers is a very fascinating idea. There was an English mathematician, his name was Dedekind. I always have a terrible time trying to pronounce his name. But he is the one that actually came up with this idea of how we could define irrationals. And it's one of the few, if not the only definitions where a set of numbers is defined by what they're not. So by definition, an irrational number is not rational, which means it cannot be written as a fraction. So examples of irrational numbers are numbers like pi. That's the ratio of a circle's circumference to its diameter. All circles have that property where if you take the circumference and divide it by a diameter, no matter how big the circle is, you always get the same number, pi. So it's a special number. Square root of 2. That's a very interesting number as well. That there was the Pythagoreans drowned a Hippocus because he proved that this number existed, the square root of 2. The Pythagoreans did not believe that irrational numbers were numbers. They thought all numbers could be written as rational numbers, or all numbers were rational numbers. So when Hippocus showed that this was a number that existed, Pythagoras got pretty upset, and the rumor is, or the myth is, that he drowned his student. In any case, that's it for this video, so I'll see you next time.